and this is sigma, and this is row composition sigma. For example, if it is AC and it contains BD, then it must be AB and BC, and you say like this, BC and CD, and you say BB and AA, it is CC, it is DD. See, this is in Bx, and this is in Bx, and this is in Bx. Just this is an example of subrotic example of the composition of two relations. See, A comma C is Bx. So you see that there exists B such that AB belongs to rho and BC belongs to sigma. BD is in row composition sigma. So there exists some in between element, that is BC is in rho and CD is in sigma. So that was the supporting example of composition of binary relations. And also, you see that if you define tau as AB, BB and CB. See, this is partial map. Partial map is basically defined by this is the collection of all partial maps. Collection of all partial maps. This is the collection of all binary relations on X set X, and this is the collection of all partial maps on set X. Correct? So you see, B have unique image, A have unique image, C have unique image, all have unique image. But if you talk about converse of tau, you see BA, BB and BC. So you see the B element B does not have unique image. B is related to A, B is related to B and B is related to C. So it does not belongs to partial, means a relation is a partial map, but converse may not be a partial map. You see, this is the difference. If relation is a binary relation, then the converse of that relation is also a binary relation. But if you talk about the partial maps, this is a counter example. You see, this is partial map, but the converse of tau is not a partial map. So now we prove one thing, that that set of partial maps is sub-semigroup of proposition 1.42 Px is sub-semigroup of set of all partial maps is sub-semigroup of set of all binary relation. Of course, it is a subset of clearly Px follows associativity as Px is a subset of Bx. See, all the members of Px are the members of Bx, and Bx is what? Semigroup. So being semigroup, it will follow associativity law. So associativity law is followed. What we have to prove? We have to show that row composition sigma belongs to Px for every row comma sigma belongs to Px. This we have to prove, basically. Correct? So what you do for this, for any x comma y1 comma y2 belonging to x, you take x comma y1 and x comma y2 belongs to row composition sigma. Now what is our claim? Claim is what? y1 is equal to y2. This is our claim. Correct? So when x comma y1 belonging to row composition sigma, what does it imply? It implies that there exists z1 belongs to x such that x comma z1 belongs to row and z1 comma y1 belongs to sigma. X comma y2 belongs to, it implies that x comma z2 belongs to row and z2 comma y2 belongs to sigma. Now you see x comma z1 belongs to row, x comma z2 belongs to row. X comma z1, x comma z2 belongs to row implies z1 is equal to z2, since row is a member of Px, that is row is a partial map. So z1 is equal to z2, you just assume as z, say z1 is equal to z2 is equal to z, say for example. Now you put the value here, z here, z here. So now what we have, z comma y1, z comma y2 belongs to sigma implies what? y1 equal to y2, since sigma belongs to Px. Correct? So it means that it implies that row composition sigma belongs to Px. So it means Px is closed with respect to the operation, and also it is associative. Hence Px is sub-semigroup of Bx. Proved. Now proposition 1.4.3, page number 18. If phi psi belongs to Px, then domain phi composition psi is equal to image phi intersection domain psi phi inverse image phi composition psi is equal to image phi intersection domain psi into psi. And for every x belongs to domain phi composition psi, see, it's a good result. Domain phi composition psi, you have to prove image phi intersection domain psi bracket close phi inverse. Image phi composition psi is equal to image phi intersection domain psi bracket close psi. And then third part is for every x belongs to domain phi composition psi, x phi composition psi is equal to x phi psi. Correct? So this part I left as an home assignment for all of you. I will do this one and I will do this, isn't it? Because this is to prove this, it is same like that. Same technique is involved here. So try to teach your mind and try, all of my students, try to by yourself this part. See how I am doing this. By seeing this, I hope all of you can do by yourself. Okay, and I will do this part. So first 3 parts are there. I will do 2 parts and left one as an home assignment. Now let's start proof. Okay, so what we have to do, you have to prove domain phi composition psi. You see phi psi are the partial maps, remember. So you start. Take any x belongs to domain phi composition psi. Of course, remember, whenever you have to prove 2 sets equal to each other, that is, you have to prove set A is equal to set B. What is the general manner? What is the approach? You take an element in arbitrary element in set A and show that it goes in an element in set B. Then A will be subset of B. Conversely, you take an element in set B and show that it goes in element A. It goes in set A. Then B will be subset of A. So in this way, set A and set B becomes equal together. So we will apply same. We will approach in the same manner, correct? So take any x belongs to domain phi composition psi. It implies what? There exists use y belongs to x such that x comma z or x comma y belongs to phi composition psi. It implies there exists z belongs to x such that x comma z belongs to phi and z comma y belongs to psi. Correct? Now it implies that z belongs to, now you see, so x comma z belongs to phi. It implies that z comma x belongs to phi inverse, converse of phi. correct? Converse of phi. And from here what you can say, and also you can say one thing, that element x belongs to domain phi, and you can say that z belongs to x comma z belongs to phi. So what you can say from here, that z is on the second slot. It means that z belongs to image phi, and here z is on the first slot, so it means z belongs to domain psi. So z belongs to image phi intersection domain psi, you can see. So here z belongs to, it implies that x belongs to z phi inverse. X belongs to z phi inverse, so it implies that x belongs to, see, z phi inverse, and z phi inverse is a subset of image phi intersection domain psi phi inverse. So you can say that x belongs to image phi intersection domain psi into phi inverse. So in this way we have proved that, it implies that you have proved that domain phi composition psi is a subset of image phi intersection domain psi phi inverse. Correct? So now we do the converse part. Now x belongs to, take any x belongs to, conversely image phi intersection domain psi. Oh, it's phi inverse. Now it implies what? It implies that x is equal to z image phi intersection domain. It implies that x is equal to z phi converse, where z belongs to image phi intersection domain psi. So from here we can write that zx z comma x belongs to phi inverse, and you know, then z comma x belongs to phi inverse. After that x comma z of course will go to where? Phi. Now you see z belongs to domain psi, so it implies that z comma y belongs to psi, of course, because z is in domain psi. So z comma y belongs to where y belongs to x. So x comma z belongs to phi and z comma y belongs to psi. So it implies that x comma y belongs to phi composition psi. So it implies that x belongs to domain phi composition psi. So in this way we have proved that both sets are equal to each other. So now image phi intersection domain psi bracket close phi inverse is equal to domain phi composition psi. So it is proved. Finally, we proved this for every x belongs to domain phi. So X belongs to domain phi composition psi, it implies that there exists Y belongs to X such that X comma Y belongs to phi composition psi. Of course, it implies that there exists Z belongs to X such that X comma Z belongs to phi and Z comma Y belongs to psi. Now observe that since phi, psi and phi composition psi belongs to Px, all are partial maps. So all of have unique images, that is X have unique image Y, X have unique image Z, Z have unique image Y. So we can write therefore Y is what? X phi composition psi, and Z is what? X phi, and Y is what? Z psi. Now put the value of Z here. So Y is equal to what? X phi into psi, and also this is equal to X phi composition psi. So in this way, third part is also proved, and this part I left for all of you. So this is all about today's lecture number 9. So in next lecture we will discuss some more results, that is proposition 1.4.4, proposition 1.4.5, and we'll start equivalence relation. So in the next lecture we start another topic, that is equivalence relation. So we stop here. Thanks.